Okay, everyone, let's get started. It's a bit after 10. Um, so good morning. So today's a big day. We're going to talk about some really fun stuff and something that will definitely stick with you for a long time. Um, Patricia's office hours are today 1 to 3. And so thanks everyone for your feedback on the course from the quiz yesterday. It was really nice to see all the wonderful, kind comments about the tutors and about the course. And I noticed lots of nice comments about Patricia and how helpful she is. So I told her and actually shared the comments with her, and she was very grateful. And she would like for me to pass on a thank you from her for these kind words. She's a very good friend. Yes, okay, Long, I'm actually going to take a screenshot of that. It's an awesome comment. That's getting sent to Patricia. So so we're all, so I should remind you, we're all actually friends. And we really enjoy this. So thanks everyone for being so wonderful and so kind. It's really encouraging to get this feedback. Regarding the pace, so we there were a few comments about the pace of the lecture, the pace of the course so far, how quickly you're making through the material, and most people, I shouldn't say most people, but more people who mentioned the pace are bored than there are people who are confused. So in other words, more people would like for the pace to be a little bit faster. I think most of the juniors and seniors are a bit bored. So 9th and 10th graders, I'm going to just slightly pick up the pace. I'll spend a little less time reviewing things. I think once I introduce a topic, I'll go through it slowly the first time, sort of the way I've been going. And then I will not continue to sort of show you algebra things, show you the basics. I'll sort of assume that those things are learned. So the pace might increase just slightly. I don't want to leave you behind, the 9th and 10th graders. Homework 4 is due on Friday at 9 p.m. and it is available online. I'm sure someone will ask for the link at some point. So anyway, so any questions about the organizational sort of part of this course so far? Anything at all? No. Okay, so let's summarize what we learned yesterday. So there were 3 important properties, and I'm going to call on people. Let's see, Isaac, we talked yesterday a little bit, so I know you were there. Isaac, what was one property that we learned?
The first property is a I don't know how to.
So it's okay. This is actually the best part of trying to explain something, trying to find the right words. So what were we taught? What was this sort of big picture, Isaac? What was the big topic of yesterday?
Exponents.
Exponents. Good. And so you remembered that. Okay, that's good. So what happens? Let me ask you. What happens if I have? I'm going to use the Greek letters. Okay. I don't even know if this is the properties in order on the worksheet, but it's okay. We'll cover all of them. Okay. Can you tell me what this would equal? This is alpha, beta, and gamma.
That would equal a a over no a
To the power.
x a to the power of
So this is
what is
beta.
that?
Sorry. Okay. You know what? We're not using Greek letters. I think it's needless.
Sorry.
Here. Okay. So this is a to the power of b, all to the power of c. And we said that this equals something. Do you know what that something is?
I forgot.
Okay. And what do you do with the exponents when they're in this order?
Add.
That's a good guess. Can anyone help? So you multiply them. And Isaac, here's a good I'm not going to prove this to you, but I'll give you an example that will make sense. So it turns out this is B times C. And the example that I gave yesterday was like, let's see. I'll use A.
It's like parentheses where you multiply B times C. Like B is in parentheses.
B is in parentheses.
Because you wouldn't multiply the A. The A would be left alone because there's no like big letters, and then is B times C because there's parentheses.
So you don't actually need parentheses here. So what this is saying is that when you have say you have A squared, okay, and then you want to cube it, you don't have to do A squared and then cube it. You can just do A to the 6th because 2 times 3 is 6. That's exactly what this is saying. So does that make sense? I'm not sure what you mean by parentheses. Were you talking about this part or this part?
I think she just meant like B and C should be in parentheses, which is the same thing.
B and C should be in parentheses. Okay. I don't think you need parentheses.
You don't.
Okay. I'm not sure exactly what that last person was saying. So, okay, but does this make sense? So, and here's the sort of, it's not a proof, but it's an example. Okay. So if I had A squared to the 4th, say, well, this is just, what would X to the 4th be? Well, that's just X times X times X times X. And replacing, X for A squared, right? That's the substitution I made here. I would have A squared times A squared times A squared times A squared. And this is just A times 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 A, which is A 8 times, which is the same thing as A to the 8th. And that is indeed equal to 2 times A to the power of 2 times 4. So this is like an example of this in action. Okay, good. Thanks, Isaac. Okay, can someone tell me the second property? And we actually almost discovered it just now. Let's see, I'm going to call on someone. I enjoy calling on people. Let's see, Monica. Okay, no Monica. Niat. Is that how you say your name? Niat? We can ask to unmute. Okay. Well, people are not seeming to participate. Anyway, does anyone remember the second property? Okay, Monica.
I don't know like the properties in order, but can I just like
go for it? Just go for it. Yeah.
So A to the power of B over A to the power of C equals A to the power of B minus C.
Great, thanks. And was that Aruhi?
Yes.
Great, good job. That is very correct. And again, we showed this with some numbers yesterday. I'm not going to do it right now because you can just go back and watch yesterday's lecture. It's on YouTube. And then for the last property, I think Monty, yes, and it did here, yes. A to the B, and I really don't even have to write it, but I will. A to the B, A to the C is A to the B plus C. So when the bases are the same, and you're in there both in a multiplicative relationship, you can add. When the bases are the same and they're in a divisible relationship, you can subtract. And then when you're taking an exponent to an exponent, so you're raising one thing to an entire new exponent, then the exponents multiply. So you can see sort of where there's like a degree of abstraction, right? So we learned how to add before we learned how to multiply. Well, now we're learning how to do exponents, and this is involving multiplication and addition. So you can see that we're sort of generalizing the things that we learned long ago. So let's use these properties in this example. So this is sort of review of yesterday still. How would I go about this?
Square root, like multiply that same equation by 3 if you're doing it like the actual way.
Okay, I'm not sure.
So take the entire inside of the parentheses and like multiply that by 3.
Multiply that by 3.
Like multiply it by itself by like 2 more times.
Okay, so how is that?
So like it's that square root of those math times square root of math times square root of math.
Okay, sure. And then what would I have?
You would have.
Okay, you want me to write it?
Oh. Yeah.
I'm afraid of what you're doing. but it's okay. This is what okay, let's just see how it goes.
A to the fourth.
Ooh, good catch. Thanks. Okay, so this is what you wanted.
Yeah.
And then I'll copy this part down. Okay, now where? What should I do?
If you combine it, it'll be a root to the what is it? Root to fourth. It'll be like the fourth root.
The fourth root.
Yeah.
I don't think so.
You multiply the three roots together, it'll get the fourth root.
That's not how that works.
Or you can just like square root all of those and then do it.
Yeah, so instead of expanding all this stuff out, let's use our new notation, right?
Yeah.
So okay, so this is, thanks for participating. This was a good place to start, but you can see that things got really ugly and really messy. And the point is to get, this should be the messiest it gets in a sense, okay? So I'm gonna rewrite this. I'm gonna rewrite the radical as the power of 1/2, okay? So note that, remember, this little property, right? This is sort of definition of the radical in terms of exponents. And so this entire radical can come out. So this is just, you know, here, I'll just write it. Sorry. To the 3/2. So the radical contributes a factor of 1/2, and this 3 is already out there. So that's how I got this 3/2. And then I have this. And now, what is now which property do I use according to the way I've defined this? How do I simplify this part? What do I have? I have exponents raised to exponents. Well, that's property 1. Why is this so slow? Oh my gosh, this computer. Sorry, people. There's like a lag in my computer. Yeah, so we use property 1. So we multiply the exponents. And people are already giving me answers. But anyway, let me multiply these exponents out. So 2, so m, 2 times 3/2, well, that's 3. 4 times 3/2, what is that? That's 6. T, so 6 times 3/2, what is that? That's 9. 8 times 3/2, what is that? It's 12. And look, now I'm copying this down. And now which property do I use? Look, I have common bases, and they're in a multiplicative relationship, so we're going to use property 3. So m cubed times m to the negative 2, well, that's just m to the 1, or m. Look, see, I'm adding the exponent, 3 minus 2. Same thing with a. See, a, 6 minus 5, so 6 minus 5 is 1, so a to the 1, or just a. T to the 9. So you get the pattern. You see how I engineered this problem. It just spells math. Okay, any questions about this example? Yes, it's the obvious answer. So I like giving problems like this because you know what you should get, and if you don't get it, you can check. So there's no reason to get it wrong in a sense. Okay, great. Any questions? We used all the properties here except for, well, we used 2 of the properties here. Okay, how about this? Even better, right? Can someone tell me how I could proceed here?
Use the second property.
Use the second property. So let's see how I don't even remember how yeah, so we have exponents in a divisible relationship. And so before I use the second property, I'm going to rewrite.
Yeah, root it, yeah.
So I have this. Okay, so I'm going to introduce something to you. When you write something, you can't
simplify on the bottom. You can't root the bottom.
Okay, I'm just going to show you a little trick. So I'm going to call the numerator a, so I don't have to rewrite all of it, because this is kind of a pain to write. And this denominator can be rewritten as
a conjugate, right?
No, I know what you're talking about, but here, okay, we're going to talk about the conjugate later, of course. But here, I'm just going to rewrite this as, instead of this radical, I'm going to rewrite it as an exponent. The radical will be written as an exponent. And how would I do that? Well, it's a square root, so the exponent is 1/2. And now, this
oh yeah, that works.
Sorry?
Yeah, that's the other way to do it.
Yeah, this is
It's the
yeah,
faster way.
sure. So to me, I don't really think when I see these types of problems because it's sort of okay, like, you know, I think exponents are really easy to work with instead of, thinking of square roots and squaring square roots and all that stuff. So there might be another way to do this, but to me, this is sort of path of least resistance. Okay, so we have a here, which is this chunk, this numerator. Now I'm going to rewrite the denominator in a way. First of all, I'm going to simplify this denominator. So all these things will get multiplied by 1/2, but by property 1, right? Property 1 says that a to the b to the c is a to the b times c. So by property 1, I have a over f to the third, right? 6 divided by 2, r to the 5/2, I to the 2, e to the 3/2, and d to the 1/2, s to the 1/2, right? And then a is up top. Okay, now how do I merge the numerator and the denominator? See, I have common bases. So this is the numerator. Now I'm substituting a back in. 3, 4, 5, 6, 7, 8, 9. And I have this stuff in the denominator, right? In fact, there's a good way to do this. Watch this. I don't have to rewrite this stuff. I can select. Did it work? No. This would be really nice if it pasted where I wanted it to. Oh, okay. Sorry, people. It doesn't work quite as okay. But how do I combine the numerator and the denominator now?
Use the second property.
Use the second property, yeah, which says that when you have two bases in a divisible relationship, the exponents do what?
Subtract.
Subtract. And so that's exactly what I'm going to do. This is a divisible relationship, and I'm going to subtract the bases. I'm going to subtract the exponents of corresponding bases. So 3 minus 3, well, that's 0. So the f's are gone. R, so 4 minus 5, well, that's -1. So I'll write it all in the numerator. So r to the -1, is just 1 over r. I to the 5th divided by I squared, well, that's, I cubed. E to the 6th minus e to the 3/2. Well, what is that? That's 4.5, which is 9/2. So e to the 9/2. And so this is really for you people, okay, to just get a lot of practice to it. You see the intention of this, right? I won't keep talking through this. This is 7.5 or 15/2. And sadly, this one does not spell a word. Sorry to disappoint. And then let's see, 8.5 is what? 17/2. Okay, so this does not really spell a word. But the point, if this was confusing to you, write this problem down, and try to do it on your own. This is great practice because we use lots of properties here. We use property 1, we use property 2. Okay, how about this? First of all, I should ask, any questions? Any questions about anything I did here? Yes, there are no friends without F's. Very good. Okay, how about something like this? So, should you freak out? Yes or no?
No.
And why not?
I mean, the roots, there's a lot of them. It basically just boils down to, like, if you replace the roots with like a 1/2, it just becomes like really simple.
Very good. So this is, you might be familiar with like the hall of mirrors kind of effect. So if you have two mirrors, I'll try to draw this well, but if you're standing in between two mirrors, you'll see an infinite regression of your image, and it keeps going back. This is what this reminds me of, right? Because it seems like it's hopeless, right? You have so many things that it's appearing to go on to infinity. This is actually not. This is a finite sort of thing. Anyway, that's just what it reminds me of visually. But each of these square roots can be written as something as the thing inside of it raised to the power of 1/2. Remember that the definition of the square root of x in exponents is x to the 1/2. And so I would work. So yeah, so people are already sort of giving me answers. Nishan, I have a feeling that's not right. I have a feeling, but let's see. I'm going to start from the inside. Okay, so x squared. Well, the square root of x squared is x, right? So this little part, this is x. And then how many square roots do I have? Well, I have 1, 2. In fact, okay, let me show you even. Here's a way you don't even have to think. Just count the number of radicals. These are all square roots, so just count the number. And I'll use the green pen for this. 1, 2. This is like Sesame Street, you know, where they make you count with the vampire guy? This is exactly what it. 1, 2, 3, 4, 5, 6, 7. So there are 7 radicals, right? And so x squared, and then I have to do this 7 times. So I'm writing something equivalent. So 1, 2, 3, 4, 5, 6, 7. Okay, now I'm going to go back to the chat and I'm going to ask Nishan. You said x to the 1/14th. That's what I assume you meant. Is that right? So someone else gave me the right answer. X to the 164. So x to the 14th is wrong because you've confused property. You've confused, okay, let me go back up here. Sorry. You have confused property 3 with property 1. See, in this problem, we have a bunch of things, like x to the 1/2, to the 1/2, to the 1/2. You know, we have a bunch of things raised with exponents themselves raised to exponents, raised to powers. We don't have common bases. So you've added the exponents when you've needed to multiply them. Do you see your mistake? So this is the same thing as x squared to the, well, how many of these 1/2? So really what we need to find is 1/2 to the power of 1, 2, 3, 4, 5, 6, 7. And 1/2 to the power of 7 is actually not 64. It's twice 64, but because of this 2 here, you know, one of these 1/2s cancels and we're left with x to the power. So the final answer is x to the power of 1/2 to the power of 6. So this is truly a transcendental problem because we have exponents within exponents. And 1/2 to the power of 6 is 1/64. So that is the final answer. Any questions about this? So I'm going a little bit faster. I hope I'm not leaving 9th and 10th graders behind. Does this make sense? Writing things, no. Okay, no. Rosie, I assume you mean no questions. Okay. I hope this is clear to people. Okay. And remember, the office hours are right after, you know, at 1 p.m. So if this doesn't make sense, you know, look through your notes, go back. And okay, here's a similar question. I'm going to do exactly what I did the first time. I'm going to rewrite all these radicals as exponents, and I'm going to use my exponent rules. So starting from the inside, I have b to the 5th. Well, the 10th root, what is the 10th root as an exponent?
1/10.
Yes, so it's b to the 5th raised to the 1/10. And now that entire thing is raised to the 1/3, and that entire thing is raised to the 1/2.
Wait, isn't it raised to 3? Because
you're
it's
absolutely right. It is raised.
There's roots there.
I made the same mistake. I got carried away. Yes, it is right. So okay, my bad. Okay, I'm gonna have to explain myself because I made that mistake. What would this be? So generally, the nth root of x is x to the 1 over n, and so using this property, this is x cubed. So thanks, Arut. You really saved me there. That would have been bad. Okay, then all of this is raised to the 1/2. Well, that's the same as 2, right? Squaring. All of that is raised to the -2, and so that would be raising to the -1/2. And then all that is raised, square root of all that. I have another 1/2. Cube root of that 1/3. So you can see now. What do I do with all these numbers? Which property do I use? 1, 2, or 3? According to the way I define the rules today, it's this property. I won't even go up, it's a pain. According to the rules I use today, it's this property, right? the one that Isaac told us. And applying that here, this means I just have to multiply all these numbers. This is just multiplying fractions. This is what you people did in like, I don't know, like 5th, 6th grade, maybe even earlier, maybe 4th grade. So this is your exponent of your final answer. And this is, this 5/10, well, that's just 1/2. This cancels with that. This cancels with that. And you're left with -1/4. And so your answer is b to the -1/4. And you could also write this as 1 over the 4th root of b if you wanted to, using your exponent rules. Any questions? So these are kind of big examples, and the reason I've given these is to get lots of practice. So ideally, you should be sitting on your end at home with a pen and paper doing this with me, okay? Watching me do these is not going to be as helpful as like doing them. Okay, so you're going to get some more practice on the homework. I don't think any of them are as ugly. I mean, these are pretty gross, okay? Yeah, so you get more practice on the homework. Go to office hours if you have questions. Okay, so the main actual topic of today's lecture, so that was sort of a long review, a long way to talk about what we did yesterday. The real topic of today's lecture is what happens when we apply this notion of exponents to functions. And so here is a function, y equals 10 to the x, okay, that uses an exponent. And here is the exponent. You can see that x is in the spot of an exponent. And so I have some questions for you. The same questions I asked when we talked about linear functions and quadratic functions and all that stuff. What is the x-intercept of this? What is the meaning of the x-intercept if we were to graph this thing?
It's where the line crosses the x-axis.
Very good. It's where the line crosses the x-axis. And what is true about the x-axis? In other words, how do I find the x-intercept? That's what we did all last week.
Negative b over n.
Okay, that's for linear functions. And where did that come from? That came from setting y equal to 0, because the x-axis is defined by the line y equals 0. So if I set this thing equal to 0, any x that satisfies this equation, 0 equals 10 to the x, any x that satisfies this is a solution or is an x-intercept, right? But I guarantee you, you can search the entire universe. As I always say, you can search the entire universe. You can go to the ends of the galaxy. You can look for your entire life for x's that satisfy this equation. You will not find one. And we're going to see why. But it turns out that this type of function does not have an x-intercept. Okay? And we'll see why in just a bit when we plot things. Can someone tell me what the y-intercept is? What is the y-intercept? Well,
1.
It is 1, and how did you figure that out?
Because anything to the power of 0 is 1.
Yes, and how do you know, why'd you use 0?
Because that's how you find the y-intercept.
That's exactly it. Yeah, so the y-intercept is defined by the line. The y-axis, first of all, the y-intercept is the point where the function crosses the y-axis. And the y-axis is defined by the line x equals 0, because x does not have any value on this line. And so setting x equal to 0 in this thing gives you y equals 10 to the 0. And 10 to the 0 we talked about yesterday for quite a while. Anything to the 0 is 1. So the y-intercept is 0, 1. So we can put that point down here. I'll put it right here, okay? Oops. Everything was going fine, and then the entire screen moved. So this is the point 0, 1. Okay, now let's use some other points. Let's make a table to sort of understand the rest of the behavior of this graph, what it looks like. Is it a line? Is it a parabola? Is it something else? So I'm going to put in some points. Okay, so -2, -1, 0, 1, 2. Those are always good options.
I don't know what you're talking about.
I'm going to mute people.
Oh, el codito rosa es un Nintendo.
Okay, so I just muted everyone, so if you have to talk, you'll have to unmute yourself. Okay, so -2. What is the y value? The corresponding y value when x is -2, well, that's 10 to the -2, and that's just 100th, right? The y value when x is -1 is 1/10. The y value when x is 0 is 1. The y value when x is 1 is 10. And this is 100. So, okay. So I assume people can plug in numbers and evaluate exponents because this is what we did yesterday mainly. Okay, and now if I plot these points, I have some idea of what the graph looks like. So -2, that's probably here somewhere. 100th, well, 100th is just above the axis, right? Just above the axis. It's really should be even closer the way I've drawn the scale. Okay, -1, 1/10. Well, that's a bit above, but still way less than 1, right? Way less than here, up here. And then 1, 10. Well, that's way up here. So 1 and then 10. And then 2, 100 is way off the graph. So I know that the graph goes it shoots up afterwards. And if I connect these points, I get this shape. And I'm sure you are all familiar with this shape. What is this? It doesn't have a name, actually. But this is the shape of exponential growth. And when people study populations or economics, or the growth of technology over time, this is the general shape of that growth. Or even, the virus that's going around. Viruses, yes, exactly, Long. Viruses grow, and all populations actually follow exponential models. So, yeah, viruses, and hopefully this is not the trajectory of the virus, right? So people were talking about flattening the curve, right? And we might spend some time at the end on Thursday talking about logistic functions and what flattening the curve means. In fact, that would be thanks for reminding me. That would be really fun. Anyway, so you can see, is there an x-intercept? Well, the graph approaches the x-axis and it gets ever closer as you go to the negative x direction. It gets so close, right? It just grazes the axis, but it never touches the x-axis. Therefore, there's no x-intercept. Even though at x equals -infinity, the function is basically at y equals 0. See, if you put in -infinity here, well, 10 to the -infinity, that's just 1 over 10 to infinity. And 10 to infinity is a huge number. So 1 over 10 to the infinity is basically 0. But technically, there is no x-intercept. Okay. And on the other end, when x goes to positive infinity in this direction, right? The function has drastically different behavior. It shoots way up. It also shoots up to infinity. So the function on this side is unbounded, and the function on the other side is bounded. These are just kind of vocabulary words that we use, okay? So anyway, so does this make sense? This is just the general shape, and we're going to be drawing a lot more of these. Let's do another example to get people more familiar with how these graphs look. 2 to the x. Okay, I'm going to put in -3, -2, -1, 0, 1, 2, 3. Okay, so -3. Someone tell me what the y value is at x equals -3.
1/8.
1/8, very good. What is the y value when x is -1/2? Anyone?
A fourth.
A fourth. What about -1? Well, that's just a half. What about 0?
0.
No.
Oh, sorry, what?
1. 1. What is the y value? 2 to the 1.
1 is just 1/2 again.
No, it's 2. 2 to the 1 is 2. Okay. I think we're losing. I think we're losing Audi people. I think we've lost him.
Okay, sorry, I wasn't paying attention. That's 8.
It's okay. It's okay. Thanks for participating, at least. Yeah, and this is 8. Very good. You've redeemed yourself. Okay. Okay, so I'm gonna graph this behavior. So -3, that's out here. 1/8. -2, that's somewhere here. 1/4. -1, 1/2. 0, 1, 2, 4 should really be out here. Sorry, I forgot the point. 1, 2. 1, 2, then 2, 4. And so this is just a sketch. Don't take it literally. Something like that. Okay, and this is the point 0, 1. How does this graph compare to this graph? How are they similar? How are they different? Do they share a point?
Yeah, they share the 0 and 1.
They share the same y-intercept. The y-intercept is the same. And generally, if you have an exponential of this form, be it y to the 1,000, y equals 10, 1,000 to the x, or y is pi to the x, or y is e to the x, whatever the base is, all of them, if they're of this form, they all share this one point. So if I were to graph the full family sort of exponentials of this form, you would have all sorts of graphs with different behaviors in the long run, but they would all be going through this one point. They share this one point. It's like, I feel like there's a good analogy for this, but I can't really think of one. It's like something they all share. It's like a common family root. It's like a common grandparent. They all have this one thing. Okay, so anyway, this is the general shape. And now we can apply sort of our previous understanding of graphing, which was one that involved this notion of, what was it called? I forgot the word for it. Like translations and dilations, right? We don't have to make this table every time. We can take this as a parent function, and then we can, reflect things on axes, and we can manipulate things accordingly. I'm forgetting the word. I can't believe, I don't know why I'm forgetting the word for this. But anyway, let's just do an example of something like that. So for y equals negative 2 to the x, transformations. Thanks, Matthew. Transformations. I don't know why I'm not. Yeah, we can do transformations on parent functions. So let's do this example. Y is 2 to the x. So first of all, do we need to draw a table? No. That's the point. And I'm going to use this previous function to graph this function. And how is this different from this? How is this different from 2 to the x? Well, they just differ by this minus sign out front. And what does the minus sign do? Well, we talked about, a few weeks ago, or I guess last week when we were talking about quadratics, that a minus sign here on a function in general will just flip the entire axis, across the x-axis. It'll flip the graph across the x-axis, right? So this was my old graph, so I'm gonna use different colors. So y is 2 to the x. Well, that's the graph I just graphed. That was this guy. And it went through this point, 0, 1, and it went through this point, 1, 2. Yeah, 1, 2. Okay. That's enough points to sort of give you the idea. And now, if I flip this across the x-axis, it's just like a mirror image. And this is my final answer. See, I didn't have to draw a graph. And I know that because of this symmetry, this is the point 0, negative 1, and that this is the point 1, comma, negative 2. So this is the smart way of graphing things, right? You don't draw a table. You use your intuition. You use your knowledge of the parent function, which is y equals 2 to the x, and you just transform it in such a way that fits your new function. Okay, I assume no one has questions there. Okay. Similarly, how would I graph something like this? 2x minus 1. Well, we talked about last time, when you have this minus 1 here, all that does is shifts your graph down, right? This minus 1 is affecting the y. It's affecting the range. And if you subtract 1 from the range, you're essentially shifting the entire graph. You're keeping its shape, but you're shifting it down all by a unit. So again, I'm going to draw y equals 2 to the x. This is the parent function. This is not my final answer. This is the point 0, comma 1. This is the point 1, comma 2. And now if I shift everything down, right, applying this, well, this point just becomes what? 0, 0. And this point becomes, see, I'm just subtracting 1 from the y values. And the entire graph in turn gets shifted down, and it looks like this. So every point on this new graph is actually parallel to the corresponding points on the other graph. You can see. But yeah, it's just shifted. The entire thing is shifted downward. Does this make sense, sort of the reasoning here?
Yes.
Great. Okay, and what do you notice about this new graph? Look, it actually has both an x and y intercept, and that intercept is 0, 0. So that's kind of cool, right? We talked about how this has no x-intercept, and indeed this thing would go way out to infinity, right? So anyway, just something to note that when you shift the thing down, of course, it's going to cross the x-axis and give you an x-intercept. And what is the point? What is the y value that this new graph will not cross? See, if you go way out here, what is the point? What is the new point? Well, it's any point described by y is -1. Because earlier it was any point described by y equals 0. So this is called the asymptote. It's a line that the graph does not, it's the line that the graph does not touch in extreme behavior, right? And so like extreme behavior meaning at infinities. And here indeed, the asymptote also got shifted down by 1 according to this transformation. Okay, so we're going to spend all of next week talking about graphing. So if this is still uncomfortable to you, you're going to get a ton more practice next week. And I'm going to sort of introduce these ideas more rigorously, this idea of transforming a parent function. So if this isn't, sticking with you, no worries. Okay, so I had some more examples of like similar graphs, but you understand that all of these sort of share the same shape. 3 to the x, all that stuff, right? Yeah, so 3 to the x, pi to the x, e to the x, all of them sort of have this general shape as I drew earlier, and all of them cross through this one point. So I'm not going to do this example. I want to move on to a final sort of topic. Here was an example with, pi to the x. And so if I were to graph this, this is no different from, in the sense of the shape of the graph, this is no different from any of these things, e to the x, 10 to the x. We know that this is going to go through the point 0, 1. And another point on this graph would be like 1, pi, right? And maybe on this side, I would have -1, 1 over pi. This is kind of coming from plugging in points to this thing. But anyway, you understand that this is the same sort of basic idea. It turns out that all bases are nice, but some bases are nicer than others, in the sense that, we can pick any base that we want in an exponential function, but some bases appear in nature and they appear in math to be more convenient choices. Okay, so usually, in high school, like when you're learning logs, we like to use the base 10 system because we have 10 fingers basically, and it's very easy to compute powers of 10, like 10 to the 3 is 1,000. It just goes as the number of zeros. So that's the way you're introduced to things. But it turns out nature has this thing called the natural base. So, and that is denoted by E. So here you would have some function like 10, y is 10 to the x. Nature sort of has this number E, and it appears everywhere. And I'm going to show you some pictures, okay, of how E plays in nature. And notice, when we say natural base, the root word of natural is nature. So if you ever, forget which one is the natural base, remember that E, E is the one that pops out in nature a lot. Here are some pictures. These are all from Wikipedia. Here's a shell, okay? It turns out that the spiral arms of this shell, the way that this thing grows, the way that this thing is described, is in terms of E. So this is called a logarithmic spiral. And we're actually going to talk about, we can, maybe on Thursday, we can talk about this spiral and related shapes. But this spiral can be described by powers of E, okay? Here's another picture that looks very similar. And it's a hurricane, and this is Iceland. And you can see that this is also a logarithmic spiral. See how it's going out? It's beautiful. And it's not just some random shape. It's actually that the exact shape of this thing, the way that nature sort of ticks, is in accordance with this number E. Here's a even nicer picture of this number E in action. This is the Whirlpool Galaxy, and it's near the Big Dipper. If you're ever out in like the country and you have a telescope, I've seen this through telescopes. It's beautiful. But anyway, logarithmic spiral. So E is this beautiful number, and it's actually called Euler's number, and it has a very specific definition. And here is that definition. It's the limit as n goes to infinity of 1 plus 1 over n to the n. So what does this mean? So people have not taken calculus. People, this idea of limit might be scary, might be confusing. But what this basically means is that if I let n, go to a huge number, like a million or a billion or a trillion or a quadrillion, then this entire thing, 1 plus 1 over n to the n, that thing approaches Euler's number. And when n becomes an unboundedly large number, so when n approaches infinity, that's what infinity is, just an arbitrarily large number that can't be counted, then this thing equals E. So if you're curious, you can get your TI calculator or whatever, and you can put this in to a table, and you can set n to be huge numbers and watch what happens when n increases. This is a fun activity. So try it out on your calculator. Here is the first, I think, 50 digits, this was from Wikipedia, of Euler's number. So again, the numbers don't matter, but you can see that I can pay you. In fact, I would bet my life on the fact that there is no pattern just in the digits here. You can look through, you can keep going, you can look at the first million digits of this. You will not find a pattern in the digits. And you might remember this notion of irrational numbers. So E is in fact an irrational number. Okay, there is no pattern in the digits. In other words, E cannot be written as the ratio of two numbers. So there's a great Wikipedia page on this. That's where I got all these pictures from. The real power of E, it's going to be random to you, and you're going to treat it the same as sort of all the other bases that we use, like 10 and pi and all those other things. You're going to treat it the same, but when you take calculus, you will realize that there are some very special properties of this number. And for the seniors, I would like to sort of spend just a minute explaining to you what those properties are, okay? Because I want you to have some familiarity with this as you go into calculus. And this is good to know. This is good for people who are not taking calculus yet either. But first, let's graph this thing. So we know that it's going to go through this point 0, 1. And then here's another point, 1e, right? 2e squared, right? Here, the way I'm getting these points is just plugging things into this thing in my head. This would be negative 1, 1 over e, negative 2, 1 over e squared, so on and so forth. So it has the same general shape. But it turns out that this shape is very special in calculus, because if you take the slope, the slope at each point, okay, sorry, this was a bad graph. We're going to need a nice graph for this. If you take the slope, what is the slope? That's just rise over run. If you take the slope at each of these little points, so here, 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 and if you plot the slope, so not plotting the graph, but if you plot the slope at each point, it turns out, this is the miracle of calculus, it turns out that you'll get the same function. And for the seniors, this is a mystery, and it takes your I've thought about this for a long time. It's kind of a miracle, but this is what makes E such a beautiful number. So for the seniors, you'll learn this notion of derivative, and we sort of mentioned this last time when we found that the vertex of a parabola is at negative b over 2a. But this notion of the derivative, that's basically the instantaneous slope. It's the slope at each point of this graph. And we write the derivative as this. So this is just a symbol. You can call it dy dx or dy over dx. And it turns out that the derivative of this function is itself. So this is really this is what makes E so special. That when you take the slope at each point, you plot the slope. So here the slope is like 1. Here the slope is something else. And if you plot all these slopes, right, you retrieve the same function E. So you can take. This means that the second derivative, you can derive this again. You can take the way you'd write the second derivative is like this. Don't worry about this yet. Okay, I mean, this is just notation. I'm just trying to get you all familiar. You can take an arbitrarily large number of derivatives of this function, and you'll still get e to the x. So that's sort of what makes this such a special thing. This is really for the seniors. I just want to provide some perspective. For this course, e, again, is going to look just like another function. But it's truly a beautiful number because of this property. So next week, we're going to get tons more practice with graphing. But I hope in the examples we've done today that you've gotten some introduction to graphing based, using these transformations on a parent function. Okay, lastly, I just want to talk about the relative rates of growth of the different functions we've talked about. So I'm going to call on someone. Let's see, someone I haven't heard from. John Perry, I have not heard from you the entire course. He might not have a mic because I don't see that he has a mic. I have not heard from John. I have not heard from Ria. Okay, so anyway, maybe, okay, I don't want to waste too much time calling on people. But can people just shout out the names of functions? The different types.
Absolute value.
Okay, so that's not a function, but that's something you can apply to a function. But what have we talked about in the course? Basically, we've talked about lines.
Quadratics and stuff.
We've talked about quadratics and cubics and quartics. And these are all, I'm not even going to call them quadratics, I'm going to call them polynomials. And in fact, lines are also polynomials because they're of this form ax plus b, which is sort of the simplest polynomial. And so we've talked about polynomials, which includes lines and quadratics and all that stuff. So I'll use schematics, quadratics and cubics. Cubic.
We haven't talked about rationals.
We haven't talked about rational functions, but those are ratios of polynomials. And so their end behavior, their behavior.
And behaviors and stuff, yeah.
We're talking, this entire discussion is about behavior of infinities. Yeah, rational. For those of you who are familiar with rational functions, those don't fall under the category of polynomials, but their end behavior is that of polynomials. So in a sense, in this discussion, they fall into that category. And now we've introduced this new thing. So for those who have more experience, you have, there are a ton of types of functions. There are polynomials and there are trigonometric functions. And there are, like what we talked about today, exponential functions. And there are, what else? There are logarithmic functions. So anyway, all we've learned today is exponential functions. And all we've learned earlier in the course is polynomials. And so I have a question for you. And that question is, how do we compare their relative rates of growth? In other words, if I were to plot a line, and then I were to put an exponential, if I were to superimpose an exponential would look something like this. What do you notice about the way they grow? About the general shape?
It's like a half polynomial, I guess. Sorry, not polynomial, parabola.
It's like, okay, I can kind of see where you're coming from. Yeah, because it goes to infinity at one end, but it goes to 0 at the other end. That's kind of a nice insight. Any other observations?
The slope stays the same for one of them.
Very good. The slope stays the same. So that's generally true for lines. The slope is a constant. Whereas, the slope of, in fact, if I were to draw e to the x, the slope is definitely not a constant. The slope is actually itself, which is pretty profound. That's what I was just talking about with the calculus thing. But all this to say that, why is this not erasing? That the exponential grows when you go to infinity. Look how much faster the exponential grows than the line. See, the line, it goes at the same rate. It's like a steady train. But the exponential, it's like I shouldn't say rocket because rockets actually don't follow exponential trajectories. Alexis, yes, there is a quiz today. But anyway, this is sort of the last point I want to make, that exponentials generally grow faster than any polynomials. And even if you have a higher degree polynomial, like a parabola, if you just take your calculator and plot these things. So here's a parabola. It turns out, I should have used Desmos or something online for it. Anyway, take my word for it that if you were to zoom out of your graph, the exponential would always be winning this race on this end, right? On this end, the exponential is always losing. But we say that exponentials grow faster than polynomials generally. Okay, and you need to know this for your quiz. So any questions about sort of the way exponentials grow? They're sort of the king in terms of growth functions. They grow faster than lines, parabolas, cubic functions, quartic functions, quintic, any degree polynomial. Okay, any questions? That's really it. The quiz. Okay, here comes the quiz. Let's see here. Really was checked. Okay, there's the quiz. And I'm also sending the link to the Wikipedia page. Just totally optional. You don't need to look at this if you don't care. But here's the Wikipedia page about the Euler number, Euler's constant E. It's a really great read. That Wikipedia page is really wonderful. Okay, but if people don't have questions, I'll just hang out here and then let's